Okay.
All right, it's Constructive and Mechanized Meta-Theory, Intuitionistic Epistemic Logic by Christian Hagemeier and Dominik Kirst. Okay, go ahead, gentlemen.
All right, thank you for the introduction and reading out the titles. So we continue on epistemic logic, and both me and Christian will be speaking. So I do the introduction and then I hand over to Christian for the more formal part. So for the introduction, if you haven't heard of Intuitionistic Epistemic Logic, it's probably best introduced by comparing it to classical epistemic logic, which can be, for instance, read about in Hintika's textbook from '62. So the basic framework here is that you extend classical logic with a modality that you then axiomatize to capture your understanding of belief or of knowledge. And the crucial difference between belief and knowledge is factivity of knowledge, which is normally expressed with the reflection principle, Ka implies A. So known propositions are true. You can believe in wrong things, but you can only know true things. And now in comparison, intuitionistic epistemic logic, as introduced by Artemov and Protopopescu in 2016, starts from the intuitionistic understanding of truth, which in the BHK semantics means intuitionistic provability. And from this, they explore how knowledge and belief can be expressed. And then something funny happens, namely the reflection principle is turned around. They propose co-reflection, stating A implies Ka, which is read as from proofs we can gain knowledge by verification. And the reasoning is that from the truth of A, which in the BHK interpretation means you have access to a proof, then you can inspect this proof and by this inspection gain knowledge. So this would then yield what they call IEL minus, which is just intuitionistic propositional calculus plus co-reflection. And then if you want to, instead of just belief, express what knowledge means, you still want to have some sort of fictivity. And here the proposal is that you adopt intuitionistic reflection, which means you can eliminate from knowledge up to a double negation. So there's no chance to just from knowledge gain an intuitionistic proof again, but at least you know that it's absurd that an intuitionistic proof is absent. And this is then IEL, it's IEL minus by adding intuitionistic reflection. And I won't go into much detail of the justification for this logic. So for this, have a look at the original paper. In our talk, we're interested in the meta theory of IEL. And also the meta theory is already well studied. Already in the original paper, the authors prove soundness and completeness with respect to suitable Kripke semantics. And from this derive results like the disjunction property, admissibility of reflection, and so on. And then others continued on this. For instance, Suenzano on the semantic side established the finite model property and semantic cut elimination. And on the syntactic side, Krupski proved syntactic cut elimination and decidability. And now I want to give an example that most of the meta theory has been done without looking at intuitionistic principles in the meta theory. So the meta logic was in all papers assumed classically, in some papers more explicitly, and some a bit hidden. And I want to give the example of completeness and show that not only the authors assume excluded middle to prove it, they also necessarily do so. And for this, we assume completeness in the proof in the form as it can be proven in the framework of Artemov and Protopopescu. So if an arbitrary set of formulas entails semantically a formula A, then this can be turned into a syntactic derivation. And a simple argument shows that from this you can deduce double negation elimination, so full classical logic. And the argument goes as follows. So we assume some proposition, we assume that the double negation of it holds, and then we consider a particular set of formulas, namely the set of formulas A, given the case that P would hold. And now the idea is that if we were able to show that from this set we can derive falsity, then we know that the set cannot have been empty because the calculus is sound. So falsity is only derivable if we have a contradictory assumption. But in the second that we have shown that T contains a set, we also have a proof of P. And by this, we have shown double negation elimination. And how do we prove this derivability here? Well, we have completeness available, so it suffices to show this entailment semantically. So we assume some model of the full set, and now we have to derive a meta-level contradiction. And on deriving a meta-level contradiction, we can make use of our doubly negated assumption. Namely, now we may assume it in the positive form. And once we have this, obviously the set collapses to the full set of formulas. The assumption that the model satisfies the set gives us then the sought after contradiction. So this works. And now even if we restrict the set of formulas to something more controlled, for instance, the innumerable sets, then still we can derive non-constructive or not fully constructive principles. In this case, this would be Markov's principle. And the proof is very similar. So we assume some Boolean sequence, which potentially has a solution. And now we have established Markov's principle if we are able to get rid of this leading double negation. And for this, we again construct a suitable set of formulas. This time, given some enumeration of the formulas, we take the nth formula conjoined with its negation, given that n is a solution to the Boolean sequence. And then we do basically the same argument as above. By this, we can get rid of the double negation because we can show that the set is inhabited. And so we have established Markov's principle. All right, so although the meta theory of IEL has been well studied, and although IEL is a very nice way how intuitionistic logic can be brought to fruit, it unfortunately hasn't been analyzed constructively yet. And so the question we started with is whether this can be constructivized, whether there's a meaningful description of IEL in a constructive system. And as the particular constructive system, we pick the constructive type theory CIC, the calculus of inductive constructions, which is a pretty expressive system implementing higher order intuitionistic logic, which on its own is quite modest about choice principles, so it doesn't dilute the analysis, which might sound familiar if you have seen Yannick's talk on Monday. And indeed, using the system and by carefully formulating the results, we can establish all the meta-theoretic results from the literature without appeal to any additional axioms. And let me squeeze in a little side remark. Not only CIC is a nice tool to study IEL, it is also a way how to justify IEL, or it has already been noted by Artemov and Protopopescu that all constructive type theories that distinguish a computational layer from a propositional layer implicitly model IEL. So namely, in the case of CIC, you have computational type levels and you have a propositional universe, and there's an operation allowing you to squash types by deleting computational information into propositions. And this squashing operation exactly satisfies co-reflection and intuitionistic reflection. And so by this, IEL is, or this approach to intuitionistic epistemic logic is pretty natural to people using this sort of type theory. Okay, so our title is not only constructive meta theory, but also mechanized meta theory of IEL. And this is guided by the question whether IEL can be feasibly mechanized in a proof assistant. So we did this as well. We work in the COG proof assistant, which is an implementation of CIC. And we use this as a tool to verify all our proofs and to track all the assumptions. Then as a side product, by implementing these proofs without axioms, we get executable algorithms for completeness, cut elimination, and decidability. And we use shortcuts to handle the computability arguments that are similar to the things that Yannick talked about on Monday. And if you are not used to looking at mechanized mathematics, but you're still somewhat curious, I can recommend that you look at the PDF version of the paper. And when you're interested in one of the statements, you can just click on it. And this will then show the formal form, how this would be written in POC syntax. Okay, I now hand over to Christian on this slide. I just want to say that this is the overview of all the results that we have covered, and half of the results is mere reformulation to fit our framework, and then the rest, the more secondary results, here we had to work to make these arguments work constructively. All right, I stop sharing and Christian takes over.
Okay. Okay, so I'll start with a quick overview of how our proof works, basically. And the first step, as Dominik already said, is this reformulation. We first prove that the natural deduction system for IEL is decidable. We do this by proving first a cut-free sequent calculus decidable, basically because it's easier to prove decidability for cut-free sequent calculus. And then using the cut elimination proof, we can transfer this decidability result to the natural deduction system. We then, the basic idea behind our completeness proof is to adapt the canonical model construction to a finite subformula universe, to a finite universe, basically. And for this, we need to modify the Lindenbaum construction slightly, and can then, using decidability and this Lindenbaum construction, give our constructive completeness proof. Once we have this completeness proof, we immediately basically also get a constructive proof of the finite model property. We can show admissibility results such as reflection, because they basically now constructively, basically because they only needed completeness. And we can also follow Su and Tsano's proof of semantic cut elimination, and using a similar argument, using a similar technique, get this in this constructive setting, basically by using decidability only of the sequent calculus. Okay. No. Before I start looking at the individual proofs, at the steps, I want to quickly mention the two deduction systems we use for IEL. The first one is the natural deduction system, and the second is the cut-free sequent calculus. And we model both systems as inductive predicates, relating a set of formulas, a finite set of formulas modeled as a list of formulas in the proof assistant, and a formula to in each other. And the idea behind both the natural deduction and the sequent calculus for representations for IEL is to extend respective representations for intuitionistic propositional logic by rules which account for the additional axioms of IEL. So in the natural deduction case, we have three additional rules: one for co-reflection, one for distribution, and one for intuitionistic reflection. And the sequent calculus only has two additional rules. We basically use the same rules as Krupski. The one rule, the KI rule, accounts for both the distribution and the co-reflection axiom, and the KF rule here accounts for the intuitionistic reflection. As a small technical detail, we use the GKI system as a base here, but this is only because it's easier to mechanize decidability for this if we use GKI by Kleene instead of G3I as the base sequent calculus. And one nice property of the sequent calculus representation is that it almost has a subformula property. Why almost? Well, the GKI part has a subformula property. Here we also have the subformula property in the KI rule, but the KF rule might introduce here a K bottom, which must not be a subformula of, which need not be a subformula of gamma or A. So it's only almost a subformula property, but for our purposes of proving decidability using the sequent calculus, this is still good enough. Okay, I now want to quickly go over this first part, which is basically showing the equivalence between these two deduction systems. And as I have already hinted, for this we first prove cut elimination for the cut-free sequent calculus. And here we basically follow the classic textbooks proof by Trollster and Schwichtenberg. So the proof structure is this typical double induction on the rank and the size of the cut. And once we have established cut elimination, of course, we need to prove inversion results beforehand. But once we have this, which is straightforward, we can prove the equivalence between the two systems. And here, of course, only the direction from natural deduction to the cut-free sequent calculus actually needs cut elimination. The other direction is just induction by induction on the derivation. okay, once we have established this equivalence, we can now move to the decidability part. And here, again, this idea of a synthetic notion of decidability comes into play. So let's first take a look at how we, we formalize decidability just by saying, well, we can construct in our type theory a function taking a formula and giving us a Boolean such that such that basically this function is a decider. So f of a evaluates or gives true if and only if a is derivable in the category sequent calculus. And yes, so we do not need like a Turing machine or such as a model of computation, and can instead just once we can give such a function in the type theory, it's computable by construction. And how do we, the technical way how this function works is basically by doing, by computing the set of, or the list of derivable sequence, which are only made up of subformulas of A. And this, of course, is only possible because we have the subformula property. And what one can also note is, even though this is a single formula, if we have a finite set of formulas, basically by shifting them into an implication and unshifting them, this generalizes to like finite sets of formulas. And of course, once we have established this for the sequent calculus, we can immediately, basically using the same function, establish the result for the natural deduction system too. So this is like the first part of the proof, is the reformulation part. And let's take a look at the first main ingredient of our completeness proof, the Lindenbaum construction. And as you all very well know, the general idea behind this Lindenbaum type construction is you have a set of formulas and you extend it usually by considering an enumeration of all the formulas, and the set of formulas you get has certain desirable properties. In the IEL case, you get prime consistent sets of formulas which are closed under derivability. And what we do here, well, we modify it to only apply to a subformula closed to a finite subformula closed set of set U. And these finite sets, again, we represent these as lists. So it's just a list of formulas, basically. And well, which parts do we need to modify? Well, first of all, we cannot get like full primeness. So primeness just means when A or B is in the set, in the resulting set in gamma, then also one of the disjuncts in it, but we only get primeness restricted to the subformula universe. Similarly, of course, we cannot get like full closure under derivability, but only closure under derivability in this in the set of formulas U. The non-derivability of a certain formula, we can get this. There we have basically the same as in the normal construction. And how does this construction work for the Lindenbaum lemma? Well, basically, we do the same as the usual construction. We just iterate through the formulas of U, and in each step, we add a formula if adding us does not cause the extension to derive the formula we want to exclude. And the one important point here is, since these are actually now executable functions on lists of formulas. So this is since we have decidability, we can really evaluate in some sense this if statement and have a function from lists of formulas to lists of formulas, which does this extension basically. Okay, once we have this, we can now take a look at how we construct this universal model. It's basically, again, adjusting the canonical model from Artemov and Polopescu to this subformula setting. And of course, so a Kripke model for IEL generally has a set of worlds, evaluation, and we have two relations. One is just like an accessibility relation, which is used for like the implication, just as in normal intuitionistic propositional logic. And we have an additional relation, which is just used for the K, so for the modal operator. And our worlds are now lists of formulas together with in the set, we would say this is like the prime consistent U series, and we model this in the proof system. There's just lists. The words are lists of formulas together with proof fields, basically that they are prime with respect to U, consistent, and that they U series. So those are the words. The evaluation is straightforward, just membership of the atomic propositions, basically. And similarly, reachability relation is just subset, and the K relation has a slight twist. So in the Artemoch paper, you only have this downward K projection as a subset of delta. What we do here is we need to additionally, and we here need to additionally include gamma. This is the same relation as is used by Sue and Sano. If we were not to include this, and we would not be able to prove that these models are actually IL models. So once we have this set up, we can prove the truth level using basically the normal proof, which means induction on the formula, and we can account for the normally classical reasoning by noting that these are lists of formulas whose membership is decidable. So we can recover some light classical reasoning here, and of course we need our Lindenbaum lemma. Once we have proven this truth lemma, we can then come to the completeness proof, and as you notice, there are like two equivalent versions to state this. One is, well, if A is a semantic consequence, then we can already get a derivation of A. And similarly, again, using this like shifting trick, it's the same as saying, stating this for finite gamma, basically. And we'll now take a look at how we can prove this first version. So we assume that that A is a semantic consequence, and now we need to produce a proof that A is derivable. And what we do now is, well, we can just use decidability and decide if A is derivable or not. If A is derivable, we're done. Then we have the proof we wanted to get. But of course, we can also have the case that A is not derivable. If A is not derivable, it wouldn't make any sense for us to try to prove that it is derivable. So in that case, we want to prove we want to produce a proof of a contradiction. And now we can basically do the normal construction. Well, since we have this that A is not derivable, we use the Lindenbaum lemma and get a word gamma in the canonical model over the subformal universe of A, such that A is not in gamma. But if A is not in gamma, and gamma is a word in the canonical model, we can basically use this in the truth lemma, and then we have that gamma does not entail A, and this is of course a contradiction that to the claim that A is a semantic consequence. Okay, and that's already our constructive completeness proof then. Now we can also recover the finite model property. The idea is we opted for the version of the finite model property that we say, well, IL has a finite model property if we get a derivation of A, or if we can produce a derivation of A whenever whenever A is entailed in every finite model. And we can basically prove this as this is using a similar argument as the completeness proof, where we then need to establish that this canonical model is finite. And you see that we always this is essentially finite. There's a slight technical reason, as I've said, the world contains these proof fields, and that's why there's like some technical things why we call it only essentially finite. Okay, I've already mentioned that this general recipe to constructivize this completeness proof, that we've also done this for the Sue and Sano semantic cut elimination proof, basically. So they prove that directly from if gamma is entailed in the cut-free if gamma is the semantic consequence, then they directly get a proof in the cut-free sequence calculus. And the way how we constructivize this is basically the same tricks with the Lindenbaum lemma. And of course, once we have established this constructively, we also get a proof of semantic cut elimination, because if we have a derivation in the natural deduction system, we can use soundness, which we can get constructively to get here. Then we use completeness, and then we basically have the proof. Okay, I quickly want to mention some things about our Koch mechanization in the proof system. First of all, as Dominik has already mentioned, the development is structured in accordance with the paper, and you can here on the right side you have like a quick overview of the development. And the two things I want to mention is, first, that we also get a lot of these results for IL minus, and by using a type class flag, we don't even need to do the work twice, but we only need to like give the delta between the IL and IL minus proofs. And secondly, this general method for mechanizing this decidability and cut elimination proof, we believe that this method, how we mechanize this, extends to other logics, and we tried this with the classical mode logic K. Okay, is to conclude, IL, we really, our starting point was basically that IL is an interesting logic which, and convincing rendering of how you can express knowledge in an intuitionistic framework. And we were surprised that there was like no, to our knowledge, no analysis of these results in the constructive, constructive setting, and we have established this. And crucially, the Coq proof assistant really helped us not to slip up, as I guess Yannick called it on Monday, that we really know that we stayed constructive. And as future work, well, first it might be interesting to investigate if this method also applies to other logic, for example, in good loop logic. And secondly, it would also Dominik had mentioned this MP to enumerable completeness, and we don't yet, yes, I guess this is the direction which is still messing, getting only with MP enumerable completeness, and we would even have an equivalent there. That's like 2 points for future work. Okay, thank you.
All right, well, thanking the speaker, some couple of minutes for a very brief discussion. So any questions, comments? Anybody wants to step in?
What about the predicate versions of these logics and corresponding results in the predicate case? Could be more interesting because you cannot rely there on the decidability of your durability relation.
Yeah, so first order versions of IEL have been introduced also by Su and Sano. And it is right, the crucial point we make use of is decidability. And from decidability, I think for very general class of logics, you can get completeness constructively. For first order logic, it can happen that it just doesn't hold constructively. So it can be, for instance, normal first order logic already, you are, depending on the formulation, always equivalent to Markov's principle. And this might be, and I wouldn't be surprised if you look at first order IEL, then at least you need Markov's principle, even in the finitary case.
Yeah, this is a well-known phenomena when the constructive proof or intrinsic constructive proof of the completeness of the first order of the propositional intrinsic logic has been around for a while already. It's a known fact. However, the intrinsic proof for constructive completeness proof for the predicate logic, even the normal intrinsic case, meet some difficulties which Dominik basically described nicely. So there is a divide which has nothing to do with a particular formulation of IL. It has nothing to do with even with object logic in general. I like the last line in the future work slide, which is still on the screen, that they want to apply similar methods to other logic, for example, GL. And GL is normally a classical system. So the object logic, the logic of the logic of the object system which you described doesn't really matter. What matters is decidability of things. And even for classical object logics, you can try to build more informative constructive proof. And I really appreciate this effort. So I'd like to see how it works for GL. I don't see any problems in doing this using the Euro decidability trick, which also Lev mentioned. But it would be nice to see. Okay.
The first order logic case is somewhat more, so the solution to these problems that you mentioned exists in terms of generalizing the class of Kripke structures, Kripke-like structures that one considers. So there are these inconsistent worlds and things like that. So there is a result by, if I'm not mistaken, by Wim Feldman on a completeness, on a constructive completeness result for intuitionistic predicate logic. And in this case, it might be also similar methods can be applicable and yield something.
But then yes, I agree. But this is then we venture in something which becomes more and more fuzzy. What is a constructive? What are constructive methods? And so we're losing.
No, it's about generalization of Kripke semantics. It's whether Kripke models are appropriate. So in propositional case, they clearly work. In predicate case, constructively, they need to be generalized. So that's the message.
In fact, this trick for Veltman that he used for intuitionistic predicate logic even works for classical predicate logic if you generalize the Tarski semantics. We had, at last 2 years ago at LFCS, we had a paper explaining this. So there we were on the non-constructive side, and here it would of course also be nice not to find more examples where this trick works, where we can establish decidability and exploit it to establish completeness constructively. It would also be nice to find the general class or what the ingredients exactly are of the logic, such that these arguments go through. So this would be really interesting to figure out.
All right.